Now let's have a look at some fundamental routing algorithms, a taxonomy of routing, before we then go to concrete examples what we use in the internet, so that you understand the basic differences. So if we look at routing, we already saw that we can do this in a static fashion. No, not in the internet. It's too dynamic. So we definitely go to dynamic. Then we could have the choice of centralized and distributed. Centralized works for smaller networks. That works depending if you are an organization and you can really control all the nodes, then you can do some central routing. But typically we go for distributed routing. To distributed, we distribute over different nodes. For distributed routing, we still can make isolated decisions so that all the individual nodes make their decision in a somehow non-coordinated way. But our focus here is on local and global distributed algorithms. It's challenging, but that's the only way how we can handle the complexity. So yes, dynamic routing is a challenge, but the network changes quite often. We have to avoid loops, but still the routers, they act on their own, decentralized. So there's no central organization that coordinates the routing. So all the routers act, they may be organized in some company, some organization, but still we have tens of thousands of routers. They all act on their own. And the problem is that the networks do not always work the way they should. There could be a typo somewhere. And this typo then creates something strange. So in this example, a line card that drops IPv6 packets where bit 65 wherever in the destination address is set to 1. So you cannot think of errors like this. So, no one noticed this, and then something doesn't work, and you cannot simply replace the line cards, and you have to look for new line cards. And what do you do? I mean, what do you do about these types of failures? So it works somehow, but And this example, so this NANOC, North American Network Operators Group, they look at the internet and on advancement of this, the idea of an open, secure, and robust internet, and they provide a platform that, in the end, where you can exchange ideas. That's for education, empowerment of this community, and there are many, many demands of this network. So the idea is they try to help to build this internet of tomorrow. And you see this example, a simple typo, a simple dropped packets based on whatever bit. No one imagined this. So strange things may happen, and routing has to survive this. Okay, so now let's have a look into the fundamental approaches we have in the internet. We have a fundamental distributed local approach. Distributed, that means that all the nodes in a distributed fashion participate, but the approach operates on a local fashion. And one is distance vector routing based on Bellman-Ford algorithm 1957. We have a close look into this. And then we have a fundamental distributed global approach, link state routing, based on the Dijkstra algorithm from 59. So both are distributed. One operates on local information, one operates on global information. And this leads to different behavior when it comes to scalability and what we can do with it, and also the problems that come with it. Okay, so first of all, distance vector routing. So what does it mean? Distance vector routing means, well, we exchange global information locally. Okay, so what does it mean, local exchange of information? The router periodically sends a list of destination it can reach. So the router thinks I can reach a certain destination, including the cost towards the destination to the neighbors. So they simply say, okay, I think I can reach destination X via 3 hops. That's called the vector, so this list of destination and cost. And if you as a router receive this information from the neighbor. And that means, okay, I will check if my neighbor sees a destination, maybe with a shorter distance that I have stored in my database. So if I see, oh, the neighbor can reach A via 3 hops, up to now I could reach A via 7 hops, I can update this information because neighbor sees A via 3 hops. I thought 7. No, that means now I see A via 4 hops, 1 to my neighbor, and the neighbor claims to see A via 3 hops. So that's the idea. So you exchange this information with all your neighbors, and the neighbors then always update their own forwarding table. Very simple. And this distributed algorithm converges then to a state where basically all the routers have tables with the least cost path. So that's the idea. Okay, so you have information about your neighbors, you collect them, you exchange them every whatever seconds, and you can always update and see, I can optimize, there's even a shorter distance. Few slides later you will see what the problem is. But so far it sounds good. You have here in the documentation a simple pseudocode for this Bellman-Ford algorithm that does exactly this step of minimizing the distances. Here we take the minimum, so you converge towards this overall minimum. So how does it work? Example here, first of all, you initialize the routers. You see here the internal tables, very simple. Here routers 1, 2, 3, and you see that all the routers say I can reach myself at a cost 0, next hop local. That means, okay, that's me. Then we do an update. We learn the direct neighbors. What does it mean? Here, for example, R1 learns that I can reach router 3 at a cost of 3. So R1 learns if the next hop R3 cost is 3. And I learn 2, the cost is 1. So that's exactly what I learn directly from my neighbors. And the same happens for all the other routers. They learn from their direct one hop neighbor. Okay? So very simple. And in this situation, R1 thinks that, okay, if I have to send something in the direction of router 3, the cost is 3, there's no other way, and that's the optimum. Then we continue to exchange these, tables. That means that the router 2 will send this table also to the neighbors, which means that then router 1 will learn, hey, router 2 sees router 3 at a distance of 1. Okay, that's interesting. So we optimize now the costs. So you see, this good news spreads, and we have learned that, okay, I see R1 at a distance of 1. R1 sees R3 at a distance of 1. So in the end, we have 2. So you see in this example, the good news took 2 steps to spread, and then we learned, okay, now there's a better path from R1 to R3. We will not take the more expensive one. So when it comes to scalability and stability, it's always a question, how fast do good news spread and how fast bad news? So what are good news? Well, we have a decreasing weight of a link. We have a new router. The path is now cheaper, better. Bad news is we have a link failure. So if we insert a new router, we insert new paths, And that means, okay, we can learn something. Okay, so we can update, for example, if we insert a new router, we learn, router 0 is at distance or cost of 2. We can reach this router. And we have some other entries here. And then this news spread also to the other, and they see, okay, we can now reach router 2 via a certain number of hops. Again, here we can optimize, so there's this way that we first get the direct information. So first router 1 got the news of the new one, spread it over these 2 links. That means in this step, router R3 thinks, okay, R0 I can reach via 3 plus 2, 5 at the cost. Yet another step, then it's optimized, because then we learned, okay, now also R2 tells it can see R0, then I can take this path, which costs only 4. Okay? Also good news is a decrease of a link weight, and this also takes some time, because first router 1 sees this and then notifies all the neighbors, and then also router 2 notifies this again, and then we can optimize and learn. So that's the good news, and overall we can say good news travel fast, which is good. So if we insert a new router, have new paths, then if n there is the maximum length of a path, we need maximum of n steps. And typically in the internet, don't think that we have paths of hundreds of routers. Rather think of, well, maybe 10, 12 maximum. So the most well-known web page, for example, you reach via 5-6 routers. So it's not 10, 20. We will see where we use this kind of protocol. So good news, travel fast. But what happens with bad news? Bad news, that was, well, you have a link failure, or you have an increase. What does it mean? So now R1 learns from one side, it costs 5. Before that we had 1, for example. That means R2 knows I will reach R0 at a cost of 2. Now for whatever reason this is changed to 5. Then R1 gets the message from R0, now sorry, it costs 5. But it gets the message from R2, well, I reach it via 2. What does R1 do? 5 versus 2. Okay, my distance to R1 is from R1 to R2 is 1. So 1 plus 2, 3. Perfect. From left, someone tells me 5, but I can compute that if R2 sees R0 via 2 hops, for example, and I need 1 hop to R2, then I see R0 via 3 hops. Okay. So, but obviously this is stupid, because you don't go via R2 to R0, because what happens in the next step, as soon as R1 tells I see R0 via 3, R2 will update this and say, oh, now I see it via 4. Wait, you see it now via 4? I update this, I see it via 5. Oh, you see it via 5? Then I update it from, I see it via 6. Oh, you see it via 6? No, now 5 is better. You see, it takes a while before we really update the bad news. Because what we do not know is, as R1 in this example, that we take information of R2 that is based on information of myself. of R1. Because in this simple example, we only exchange the distance, but not where the distance is based on. What happens even worse if a router is down? So if the router is down, then, well, we run into a problem that is also known as count to infinity problem. Well, what does it mean, count to infinity? Well, assume, again, before the router is down, the distance is 1. Then R1 knows the distance to R0 is 1. And R2 knows the distance to R0 is 2. That's 1, it's a distance to R1 plus the reported 1. Great. Now the link is down, so doesn't exist anymore. That means we could assume this reports infinity. Okay, then router 1 says, okay, from the left side I get infinity, doesn't exist. But from the right side I get the report, oh, the distance is 2. Then I know the distance to R1 is 1, so I know the distance is 3 now to R0. Okay, router R2 now knows, okay, because the next exchange says is 3. Okay, now my distance is 4 because 3 is reported, I have now 4. So I report the 4. Oh, then it's 5. Okay, 5. Then it's 6. Then it's 7. Then it's 8. Then it's 9. Then it's 10. And so on. Ad infinitum. So the problem is, we can do this in kind of infinite, and then in addition we have the information of R3 telling us, oh well, I also know where R0 is. And the main problem is no one of the node knows that all this information is based on the initial information of R1, where the failed R0 is. So, well, how can we avoid these permanent loops? Because you see, we have this information looping. So we get the information based on my information. Now my information gets worse, then the information that is based on my information gets worse, which then makes my information even worse, etc., etc. So one way of handling this is called split horizon. Split horizon, that's one way of trying to avoid the loops. So routers, they do not propagate information about a route back over the same interface from which the route was received. So if I receive information about router 0 via this interface, I will not send back any information about router 0 via this interface. So that basically stops this problem of this count to infinity with this very simple example where we have only these 3 routers involved, one failing, then R1, R2. And then we can also add something that's called split horizon with poisoned reserve. Take this as pointer into literature if you're interested in details. So split horizon with poisoned reverse. We actively advertise routes as unreachable over the interface over which they were learned. So that's one of the ideas, but the problem is this simply does not work for all topologies. So even with this, and you can take this as an example, even with split horizon with poisoned reverse, these loops, this counting to infinity, you can construct topologies where this still exists. Because you can always construct a topology where you get the information about someone else via other interfaces than the direct interface to the router 1 in our example. Okay, so bad news, they have a problem, they travel slowly. We can apply some optimizations, these are the pointers, but the main trick, so to say, is, okay, we have to limit infinity, and we simply define infinity that's 16. That's easy. I mean, this is computer science, so we can say infinity is 16, and so we know that we have a maximum cost and we simply say infinity is 16, and so this is the maximum number of steps. Okay, but still, bad news travel slowly. And this is only some kind of artificial help that will say, okay, we limit infinity, and then we say, okay, it's unreachable if we reach this 16, which is a bit arbitrary. So that's the basic idea of distance vector routing. It's very simple. You exchange distances with your neighbors, and they are called vectors, so distance to a certain destination, but it's not robust. And we have a problem that also buggy routers can announce strange things like cost 0 to all destinations. That's one thing. And this results in nearly all the traffic is then routed via this router, and the network collapses. So that's one of the problems of this distance vector, because we believe in good news and say, oh, okay, cost 0, that's great. So this is really a short path. This router claims it has cost 0 to all destinations. Perfect. Problem. So if we have a link failure, it takes some time. So in unlucky cases, really, the link failure is too slowly diagnosed. So we have these loops due to these divergence times, and we have this count to infinity, and there were even count to infinity accidents. You can look this up in the RPNet back in 1983. So distance vector routing, this is one of the basic principles. Yes, there's a routing protocol, I will briefly touch it based on this, but it has some problems. Okay, and what is the main problem? We exchange partial information and do not know that this information is based on the information of other nodes that may have a problem, etc. So what we can do is we exchange now the local information, not only with the neighbors, so locally, but globally. Okay, scalability, that's always the issue. But still, let's have a look. So the routers periodically send the state of the links to all the neighbors to all the routers in the network. So basically, we flood. Here we have this flooding, limited flooding in the network of the states of the links. So I, as a router, tell all my neighbors, these are the states of my current links to the neighbors. So what are the costs to the current neighbors? So here we exactly have this flooding. So in the network, and this tells you immediately, link state routing cannot be used on a global scale. So maybe up to several dozen nodes, maybe 100 routers, that's it. But you cannot use link state routing worldwide. Doesn't work. So flooding is used here, and the routers, they receive the information about the links of all the other routers, and then you start building up your own so-called link state database. You aggregate all the topology, and in the end, you try to get a global view of the network. So that's the difference to distance vector, where you only see your neighbors and try to create an optimized table. And here we have this global view and then try to find a perfect path. So the router can then derive the forwarding table from this link state database. And if you have an update for the link state database, then the router recomputes the forwarding table. So if a link goes down, then you will receive this update and then recompute your forwarding table. That's the idea. How does it work in a bit more detail? Well, so the router determines the neighbors. So they say periodically hello to the neighbors. And then you see, okay, you get answers. You get answers from the neighbors and you flood this collected information also periodically, for example, every 30 seconds, via so-called link state advertisement packets to all other routers. And then you continuously update your database based on these LSA, so the link state advertisement. And if you have an updated database, then you recompute the paths based on this database. And how to compute the path? This is where Dijkstra comes in. So Dijkstra allows you to compute the shortest path based on this link state database. That's the idea. But again, this is based on flooding, and trying to compute the topology of a whole network works only for smaller networks. So what does a link state advertisement contain? In the end, we have the identification of the sender, so who sends this, so it's me, and this is my view of the world, and I see these are my neighbors, including the cost, and then a certain sequence number, because if we start flooding all these things now, sequence numbers, duplicate detection, and an age to tell me which is a newer information, because I may receive an old one. So in this simple example, we get certain packets, so we know that, for example, here from A to B, A sees B the distance of 4, and A sees E at a distance of 5. So that is the view of A. And so on. We have a certain view of B and C and D, and so on. This is the local view, but we distribute this in the whole network. And then all the nodes have now this database, knowing that, so the view of this node is this and that, and the view of this node is this and that. And now we can start calculating the shortest path. And this is just a quick overview of Dijkstra, the Dijkstra algorithm. So basically, this algorithm solves this single source shortest path problem, how to find the shortest path from a source to all other nodes or vertices. And so assuming certain properties like non-negative weights, and it's a so-called greedy algorithm. So we take as input the weighted graph with the edges and vertices, and we have all these non-negative weights, and we get this information, the initialization information, from this database. And the output is then the length of the shortest paths, or the shortest path themselves, from this given source to all other nodes. That's the idea. And I can give you a quick example. So from 1959 for this. So you mark the source node, say, okay, you start, and each node has to do this. So you take one of the nodes, for example, node A, and you say, this is our starting point. We mark them as permanent. And then you look at the neighbor nodes of the work nodes, and you compute the distance from the source to them. You have this current knowledge, you have the link cost, you start with the link cost directly, and then basically you continue and you choose the node with the smallest distance to the source from the nodes. They are not marked permanent. You take the one with the smallest distance, so you have a list of the neighbors, you take the one with the smallest distance, mark it as permanent, and set it to be the new work node. And then you repeat this if there are still nodes that are not marked as permanent. Okay, example. Then I guess it's a bit clearer. So we start here with the current working node A, and now no node is marked as permanent. And, well, we can take the delay, distance in kilometers, or whatever. So this is a very basic algorithm. You can apply them to different problems. Here it's networking. So first of all, we mark the node A as permanent. Okay? And then we look, okay, what are the neighbors? And you see clearly B now is only 2 kilometers away compared to G, for example. And all the nodes, when they communicate, they store the predecessor. So the node B knows predecessor is A, distance 2, and G knows it's A, distance is 6. And then the next step is B. Now our next node, the working node, becomes permanent. Well, it's the smallest distance. Now that's our working, that's the current working node, becomes permanent, and you continue from B. Now the neighbor nodes from B are A, that's already permanent, and E and C. Okay, now you continue because B is now permanent. We turn R to C is 7, to E is only 2. Now we make E permanent, because if we look at the distance now to A, it's 2 plus 2 is 4, okay? And 4 is smaller than 9, and 4 is also smaller than 6. So because this is also potentially a candidate, G. So E is now the one with the shortest distance altogether to A. That's the path A, B, E. Okay, now we continue with E. Now E looks at G, F, and we still have up there the C. And now we see that, okay, distance to A is now 2 plus 2 plus 1, so G has 5, okay, and F has 2 plus 2 plus 2, 6, oh, okay, and C has 2 plus 7, 9. Okay, 5 is now the smallest one, so G becomes permanent, since the distance to A is the smallest with 5. And then we continue with the neighbors of G. That's step 7. Okay. Then we see, okay, now F becomes permanent because this distance is to A is smaller, 6 is smaller than 9. Why 9? Well, look at the neighbors of G, that's H. H has this distance of 2 plus 2 plus 1 plus 4, 9. And C has 2 plus 7 is also 9. F has 2 plus 2 plus 2, 6. That's the smallest one. Okay. Then we say, okay, let's continue here with our F. We don't forget G. But now we continue with F as the working node. Okay. We continue, same step. Now we go from F to H. Why? Because here we have a distance of 8, still smaller than this 9. And we look at the neighbors now also. Here, step 13, C becomes now permanent. Distance to A is 9, smaller than 10. And continuing, distance to D using C is larger than this tentative label of D. No more paths. No states are changed. The algorithm terminates. And in this case now we see that D is reached on the shortest path, and that's it. So that's a way how we can find the shortest path, in this case from A to D. It's a greedy algorithm. It's greedy because we always can compare for each step, so which is the smallest one, take the node and continue. Now we have to do this now for all these paths to the different nodes here in the network. Okay, implementation here also, just if you want to look at some kind of code, C code for exactly this, Dijkstra algorithms. So link state routing, more complex, yes. You have to manage more state and routers, but way more stable. In case a router breaks down, link failure, we don't have the counter infinity problem because we see the whole topology. And so a wrong information from a single router typically does not crash the network. Big advantage. Distance vector, if one router lies, all the traffic goes via this router. So if we compare this link state and distance vector, we see, yes, in link state we flood topology information, so information about the neighbors. All the nodes compute all the paths, and we will see concrete protocol using this OSPF. So idea here is each node knows how other nodes may reach any other node. Distance vector, we advertise destinations and distances to destinations. There's the routing information protocol, RIP, using this. But here each node only knows how to reach any other node. But we don't know what's going on, how the topology looks like. So what you should know is the fundamental difference between distance vector and link state routing. And what is this idea of bad news, good news, and in the context of routing, and why bad news travels slowly, good news fast, and why is this bad that bad news travel slowly? And what about the scalability of the algorithms? Now consider large networks, consider dynamic networks. How do they survive? How can we handle dynamic topologies?